You have a bicycle wheel that can be approximated as a thin hoop with a mass of m and a radius of r and rotational inertia of I equals mr squared. The wheel is suspended so that the axle is parallel to the ground as shown in the picture. The wheel is free to rotate without friction. A light string is wrapped around the edge of the wheel and pulled straight down with the force F. And I'm actually going to add that on here to the diagram. So there is F there, as shown in the picture. Answer all questions in terms of givens. So what is the angular acceleration of the wheel? Don't let this angular stuff throw you off. If you have the rotational inertia, that's basically the mass, and you got a force, and they're asking for acceleration. So mass and force and acceleration, that would be Newton's second law. So let's do it in its rotational form. Instead of A equals the sum of F over m, A equals the sum of the torques over I there. Now let's start to plug in for those. So when we go to find our torque, that is going to be force times lever arm times the sine of the angle between those two, and our rotational inertia they gave us is mr squared. Well, if we look up here, the lever arm actually is the same thing as the radius of the wheel. So we can say force times lever arm, and the angle between those two is 90, so that whole sine of 90 disappears. And then down here in the bottom, we still have the mr squared, so this r cancels with one of those r's, and we wind up with, in this case, the force over the mass times the radius. Check it and see if it makes sense. More force, more angular acceleration. A more massive wheel, less angular acceleration. If you pull less far out on the radius or more far out, you would get more of an angular acceleration there. So next part here, they say if the wheel turns through 3 revolutions. Well, what is this 3 revolutions? This is basically our distance or our change in the angle there. So, and remember, 3 revolutions, each revolution is 2 pi radians, so this is going to be 6 pi radians is our change in our angle there. What will be the final, watch it here, linear velocity of the edge of the wheel? So first, let's find the final angular velocity and then change that into a linear velocity. So, look at what we've got. We've got a change in our angle, that's kind of like x. It really should specify here that the initial velocity, it starts from rest, so our initial velocity is 0. And then they're asking for what is our final angular velocity, and we just solve for our angular acceleration. So if this was our old school linear physics, we got the distance, the initial velocity, the final velocity, and the acceleration. Which equation would get us there? It's what we've often called the fifth one. So the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration, angular in this case, times the displacement, angular in this case. There is no initial velocity, so let me go ahead and write this line. The final angular velocity will be the square root of 2 times the angular acceleration times our angular displacement. So now we've got to substitute in for those values. So the final angular velocity is going to be 2 times, and we just found this, it's F over mr. And then our angular displacement here is 6 pi radians. And so we can clear that up. In this case here, we can pull out a 2 from here actually because there's a 2 in the 6. And so we get 2 square root of 3 would be left in there, pi F over mr there. That is not the linear velocity though, that is the angular velocity. So if you remember, to get the linear velocity from the angular velocity, we have to multiply by the radius. So let's do that. Velocity now is 2r, we'll have to multiply, and let me just clean this up a bit. 3 pi f m over r. And if you wanted to, you could clean that up, like you could actually move the r inside and make that an r squared. And so I'm going to do that. I'm going to leave my 2 outside here and get 3 pi f r squared over mr, and that's just to cancel that r out with one of those r's. So when it's all said and done, you get 3 pi f r over m there. So Now, what if you attach 4 weights to it? What will happen to this final speed? Well, what we are effectively changing here is our rotational inertia. So, in this case here, that's the rotational inertia. We've added mass. That's all you need to know. More mass means it will not accelerate as much as before, and our final speed will decrease. So the next question here says, compared to part C, so that's the part that we just did. I don't know what happened in part D, actually. It's missing. But compared to part C here, what if we move the masses in? Well, again, remember that the rotational inertia is the mass, but it's also where is the mass. So if we move them in, we've decreased our rotational inertia, so it will be able to spin more easily, and compared to the one that we just did, the speed will go up. And then finally they say, what if instead of pulling with the force F, what if that force F is caused by a mass? How will that change our final speed? Well, in that case, it's not just these things that are rotating, but it's this thing that's moving linearly. This mass also has inertia. It also doesn't want to move. And we haven't added any more force, but we've added mass to the system. We've added inertia, so compared to before, that rate of acceleration and therefore the final velocity will decrease.